Good day, everyone. I am Maxime Alcala, and together with my research partner, Gabriel Torres, we will be presenting our study, Compositional and Structural Analysis of the Lime-Based Plaster of the Syquia Mansion for Evidence-Based Restoration, conducted under the advisement of Professor Eric Miranda. We are Bachelor of Science in Material Science and Engineering students from Mapua University, and we hope you find our presentation insightful. The preservation of cultural heritage structures such as the Syquia Mansion in Vigan City is essential for maintaining historical authenticity. The 2022 earthquake exposed the vulnerability of these structures, highlighting the need for appropriate restoration materials. This study aims to characterize the chemical and physical properties of the Syquia Mansion plaster to guide its restoration. Through various analytical techniques, the original plaster composition will be identified and experimental plaster mixes will be evaluated to determine the most suitable formulation. The findings will contribute to heritage conservation efforts, ensuring the longevity and authenticity of the Syquia mansion while aligning with sustainable restoration practices.
Here are our objectives. Here we have the methodology flowchart for characterization of Syquia plaster samples. Here we have the methodology flowchart for experimental plaster construction and characterization.
Moving to our results, XRF was used to determine the elemental composition of the Syquia mansion plaster samples. As you can see in Table 4, the dominant component was calcium oxide, confirming the lime-based nature of the plaster. We also found significant amounts of silicon dioxide, indicating the presence of sand. To understand the relationship between these two key components, we performed linear and polynomial regressions. This figure shows a weak linear correlation, suggesting a loose inverse relationship. However, this figure, the polynomial regression, shows a much stronger parabolic trend, implying a more complex nonlinear interaction. This is further supported by our Pearson correlation analysis, which showed a moderate negative correlation between calcium oxide and silicon dioxide and a strong positive correlation between iron and silicon dioxide, as seen in Table 5. Optical microscopy examined the Syquia mansion plaster's layering, texture, and microstructure. The sample was inspected in its natural state, then embedded in epoxy, sectioned, and polished for cross-sectional analysis. Low magnification revealed a multi-layered structure with a thin lime wash over coarser layers, showing cracks and detachment. Higher magnifications highlighted a heterogeneous lime-rich matrix with aggregates, while polarized light microscopy confirmed birefringent particles likely quartz or calcite. Four applied layers over a lime plaster base suggest multiple restoration phases, informing further SEM-EDX analysis.
For the TGA results of wall 4, we observed minimal initial weight loss, indicating low moisture content. A significant weight loss between 650 and 800 degrees Celsius suggests dehydroxylation of calcium hydroxide. The limited decomposition at higher temperatures indicates a smaller presence of calcium carbonate. These results show the presence and behavior of calcium hydroxide, which complement our FTIR and XRD findings by confirming the plaster's composition and thermal stability. Wall 3 has a similar trend in initial weight loss and a significant weight loss between 650 and 800 degrees. The weight loss between 200 degrees Celsius showed that wall 3 had a higher initial moisture content than wall 4. The more significant weight loss during dehydroxylation in wall 3 indicates a higher amount of calcium hydroxide compared to wall 4. Both samples have a low carbonation level, as seen in the minimal weight loss above 800 degrees Celsius. For the DTA results of wall 4, a peak between 150 and 200 degrees Celsius suggests presence of organic additives like clay minerals, while peaks around 550 to 650 Celsius possibly indicate minor carbonates such as the dolomitic lime, which is also detected by XRD. The peak between 750 and 850 Celsius aligns with the calcium hydroxide dehydroxylation, confirming its high presence and purity. Wall 3 revealed similar information, such as the possible presence of organic additives at 200 Celsius and calcium hydroxide dehydroxylation at around 800 Celsius. It should also be noted that the peaks at 400 to 600 Celsius are likely due to the decomposition of pozzolans. The DTA results of both samples confirm that they are lime plasters that use calcium carbonate as a primary component. However, there are differences in their composition and/or aggregate. Wall 4 has organic impurities, and Wall 3 contains aggregates that react at higher temperatures, likely with siliceous materials. It is possible that one sample is from aggregate that is not as pure.
The surface morphology of the Syquia mansion plaster was examined using SEM at magnifications from 500x to 50,000x. Lower magnification showed a rough surface with uneven grain distribution, indicating a heterogeneous composition due to historical application, aging, or weathering. Higher magnifications revealed clusters of fine grains, compacted mineral deposits, and loosely arranged particles, suggesting material variations. These differences in grain size and porosity imply multiple application layers, potentially affecting mechanical properties. EDX analysis was conducted to determine the elemental composition. PDX analysis confirmed a predominantly lime-based plaster with high carbon and oxygen, indicating calcium carbonate formation. Calcium reinforced this, while suggested gypsum from environmental exposure or additives. Low silicon indicated minimal sand, pointing to a fine plaster or lime wash. Minor elements like magnesium, aluminum, potassium, and titanium likely came from impurities or historical additives. Chlorine suggested salt contamination, while titanium may be from mineral inclusions or pigments. Further cross-sectional SEM-PDX analysis is needed to study elemental distribution across layers. Elemental mapping of a Syquia mansion plaster cross-section shows the distribution of key elements across layers. Calcium dominates both top and lower layers, confirming a lime-based composition. Silicon appears in patches, indicating uneven sand distribution. Sulfur and barium are concentrated in the lower layers, suggesting historical additives or gypsum use. Magnesium is localized in the middle and top layers, possibly from dolomitic lime, and chlorine is strongest in the top layer, likely from environmental exposure. Carbon is slightly lower in the base, reflecting differences in carbonation or organic content.
For the FTIR analysis, we used a spectral range of 500 to 4,000 per centimeter. All samples showed peaks at approximately 1405 and 872, corresponding to carbonate groups and their bending vibrations, which confirms the presence of calcium carbonate as a primary component. The broad band between 3000 and 3500 indicates OH stretching vibrations, suggesting the presence of water molecules or hydroxyl groups, supporting the presence of calcium hydroxide. While all samples showed these, variations in peak intensities were observed. The data suggests that plaster samples are primarily composed of lime-based materials with varying degrees of carbonation. Overall, results of the plaster samples are relatively close, with minimal variations in wall 3 and wall 12. For the XRD results, we see similar mineral compositions for wall 3 and 4. The peaks around 29.4 degrees for calcite and 26.6 degrees for quartz prove their presence as they were used as an aggregate. Dolomite peaks at 30.9 degrees suggests impurities or the use of dolomitic lime. Smaller peaks at 40 and 47 degrees are secondary calcite reflections, supporting its primary role. Gypsum at 11.6 and 20.7 degrees were detected, which is likely from reactions due to environmental conditions where over time, lime plaster can absorb sulfur from the environment and form gypsum, while feldspar at 50 to 70 degrees may be from aggregates. This mineralogical makeup is consistent with traditional lime plaster, as peaks indicate calcite as a primary binder. The XRD findings corroborate the FTIR data, which also indicated the presence of calcium carbonate. Detection of gypsum offers insights into the plaster's alteration over time. Next, we have the results and discussion for the construction and characterization of possible plaster mixes.
Visual assessment of the plaster mixes showed varying water content based on the lime to sand ratio. The 1:3 mix required the most water due to higher sand content, while the 2:1 mix needed the least. Before application, the 2:1 mix was the lightest in color, the 1:2 mix medium toned, and the 1:3 mix the darkest. During application, the 2:1 mix was the easiest to spread due to its higher lime content, while the 1:2 and 1:3 mixes were more difficult to apply evenly. Throughout curing, cracks developed in the 2:1 mix misted and to a lesser extent in the 2:1 mix submerged, while the 1:2 and 1:3 mixes remained stable with no visible cracks. By the 28th day, all samples had dried completely, and the 2:1 mix had the most pronounced cracks, and the 2:1 mix submerged mix had smaller cracks, and the 1:2 and 1:3 mixes remained crack-free, confirming better stability. All samples lightened in color but maintained their original tone differences.
Plaster extraction was done using a metal scraper, chisel, and hammer. Plasters applied to misted substrates required more force to detach than those on soaked substrates, suggesting better adhesion with misting. Visual inspection confirmed that the misted substrates had more plaster clumps remaining, while soaked substrates were smoother. The plaster ratio also influenced extraction. Samples with higher sand content, Ma, Sa, Mb, and Sb, produced larger pieces due to the increased bulk and rigidity, resulting in a more cohesive mixture. Samples with higher lime content, Mc and Sc, produced smaller, more brittle pieces due to the inherent softness of lime. Misting allowed for a gradual drying process, which led to an even drying and resulted in uniform pieces of plaster when chiseled. Soaking the clay brick in water allowed for maximum moisture, which conflicted with the curing of plaster. This may have softened the lime component and weakened the bonds between the particles, which led to the plaster breaking down in smaller pieces compared to those in the misted substrates. The irregular moisture distribution in the soaked substrates further contributed to the lack of cohesiveness in the sizes of the extracted plaster.
The safe analysis of the sand used in the plaster showed that 51.28% of the particles were larger than 600 micrometers, indicating coarse sand and aggregates contribute to the plaster's strength. Intermediate sized particles made up 45.4%, improving packing density and mechanical strength. Only 3.42% were fine particles, reducing shrinkage and cracking. The well graded sand, confirmed by the particle size distribution histogram, is ideal for plaster applications, improving workability, strength, and adhesion. The Shore Sea Hardness Test measured six plaster mixes under misted and submerged conditions. Submerged samples generally had higher hardness, with the 1:2 mix showing the highest average hardness. The 2:1 mix had the highest hardness among the misted samples. This suggests that higher lime content improves hardness in misted conditions, while a balanced lime sand mix is more effective for submerged conditions. The 1:2 submerged mix showed the most consistent results, highlighting its strength and stability. In the misted condition, the lime effectively coated the sand grains, creating a well-integrated microstructure with moderate porosity. Strong bonding prevented shrinkage cracks, ensuring flexibility and adhesion. In the submerged condition, the lime phase was more pronounced, embedding sand grains deeper for a smoother, cohesive structure with minimal gaps. This suggests improved lime dispersion and adhesion. The misted condition showed weaker binding due to lower lime content, leading to higher porosity but better moisture permeability. Despite its looser structure, no cracks were detected, indicating flexibility. Under submerged curing, lime dispersion improved, embedding sand grains more effectively, but the reduced lime content still limited particle bonding strength. With excess lime, the misted 2:1 ratio formed a dense, rigid microstructure with low porosity. Strong binding restricted grain movement, making the plaster brittle. Although no cracks were observed microscopically, macroscopic shrinkage cracks were present. Submerged curing further intensified lime dominance, embedding sand deeper, but the structure remained stiff and prone to shrinkage cracking over time.
For porosity, samples with higher lime content MC and SC showed a significantly increased water absorption at 15.87 and 17.78% average. Increased sand content reduced water absorption as seen in sample MB at 10.90%, absorbed less water than MA at 11.77%. Samples MA, MB, SA, and SB had a lower standard deviation value, indicating consistent water absorption. MC and SC had a comparatively higher SD value, potentially due to the surface cracks. The substrate condition also contributed as soaking enhanced the effect of composition, resulting in 10.74% increase in water absorption on samples with 2:1 lime to sand ratio, with an average of 9.17% decrease in water absorption in samples with 1:3 lime to sand ratio. These results highlight the impact of plaster composition and porosity and potential durability. High lime content may increase vulnerability to moisture-related damage. These findings enhance the compositional analysis, emphasizing the importance for material ratios for plaster performance. For density, increased lime content correlated with lower loose bulk density, as seen in sample MC where its density is 1.0664 grams per cubic centimeter, which is lower than MA at 1.3644 grams per cubic centimeter, and MB at 1.3156 grams per cubic centimeter. While not always directly correlated, a 1:2 sand to lime ratio may be more effective at maximizing density, as seen in MA and SA compared to MB and SP. As for the substrate effects, misted samples consistently resulted in higher densities than soaked counterparts, even with identical mix ratios. Excessive moisture from soaked substrates may have led to lime leaching, resulting in lower densities. Density findings align with porosity results, suggesting that higher lime content influences both properties. These results contribute to a broader understanding of how varying the ratios of traditional lime plasters influence their performance. This study confirmed that the Syquia plaster is a lime-based material primarily composed of calcium carbonate, with additional components such as quartz, dolomite, and gypsum. XRD, XRF, and FTIR analysis validated its composition, while SEMEDX and optical microscopy revealed a layered structure with a lime-rich finishing coat over a sand-based bulk plaster. STA or TGA-DTA results confirmed the dehydroxylation of calcium hydroxide between 650 and 800 degrees Celsius, indicating its lime-based nature, while minimal weight loss beyond 800 Celsius suggested low carbonation levels. The presence of sulfur, chlorine, and barium compounds pointed to historical additives or environmental influences, further highlighting the complexity of the plaster composition. These findings provide a strong foundation for selecting restoration materials that align with the historical and structural characteristics of the plaster. The study also examined varying lime to sand plaster ratios to determine the most suitable formulation for restoring the Syquia mansion. The 1:3 lime to sand mix was found to be the most visually compatible with the plaster used in the mansion while maintaining adequate structural properties. Hardness testing showed that the mix's hardness also depended on the condition of the substrates, where the 2:1 mix performed the best in misted, while the 1:2 mix performed the best in soaked substrates. Porosity and density testing confirmed that higher lime content had increased water absorption and reduced density, with the 1:3 mix demonstrating the lowest absorption rates at 90.9 to 10.90%, and satisfactory density values at 1.3156 grams per cubic centimeter for misted substrates and 1.2252 grams per cubic centimeter for soaked ones. The curing process played a critical role, while misted substrates yielded higher densities. While the 1:2 mix offered better mechanical strength, the 1:3 mix is recommended for restoration due to its balance of historical accuracy, sufficient durability, and moisture resistance. These findings contribute to the heritage conservation efforts by providing a scientific basis for selecting appropriate restoration materials, ensuring the preservation of the historical integrity of the Syquia mansion. Further analysis is recommended to assess the long-term durability of the 1:3 lake lime to sand mix under real applications and environmental conditions. This should involve monitoring its performance, especially regarding cracks, exposure to high moisture due to the coastal area, and biological growth over an extended period of time. Comparison of the Syquia plaster and experimental plasters using various analysis techniques would also be beneficial to confirm the similarity of the two. Furthermore, given the vulnerability of Syquia mansion to seismic events, it is crucial to investigate the seismic resilience of lime-based plasters, including the 1:3 ratio deemed most suitable in this study. Further studies should explore incorporating reinforcing additives and improving application techniques to enhance structural stabilization against these forces while maintaining historical authenticity and breathability. Finally, a comparative analysis of the Syquia plaster with other heritage sites in the region should be studied. This would allow for the development of standardized conservation guidelines tailored to the specific materials and environmental conditions present in the vegan city and similar historical areas.